However, as the gate length decreases down to quantum limit, Moore's law ended due to the high power consumption. Thank you for giving me the opportunity to talk about my research today. My name is Sungjae Cho. I'm from Department of Physics at KAIST. Today I will talk about my recent research on low voltage transistors and diodes, which is to extend the road beyond CMOS. And some of the results, especially low voltage transistors, are published in Nature Nanotechnology and Nanoletters last year. And about diodes, it's not published yet. According to Moore's law, continuous downscaling of transistors enables today's information technology. However, as the gate length decreases down to quantum limit, Moore's law ended due to the high power consumption in the standby leakage power standby state. As you can see, it says the gate length decreases, active power, both active power and standby power density increases, but however, the standby leakage power density increase more steeply. How can we reduce this power consumption and extend Moore's law? The active power consumption is proportional to the VDD, which is power voltage, operating voltage square, and standby power density. Leakage power density is proportional to the operating voltage. To decrease both the active and standby power density, we need to decrease VDD, operating voltage. However, if you just with the same for the same IV characteristics, if you just reduce the operating voltage, then what happens is the off-state current increases and standby power density increases. So to reduce both active and standby power density, we need to reduce this subthreshold swing, so-called subthreshold swing, which is inverse slope of this IV curve. So if you look at this blue curve, this inverse slope is much steeper than the red curve, and in that case, you can reduce the offset current and also the operating voltage. So, but in case of MOSFET, the traditional conventional transistors you have been using in Moore's law, this subthreshold swing, inverse slope of the IV characteristic curve, has limitations. It cannot be lowered below 60 millivolts per decade. So alternate transistors are required to reduce this subthreshold swing below 60 millivolts per decade. Also, in diode also has some fundamental limitation of thermal conventional diode. So how steep this curve, this IVG curve in transistor is represented by subthreshold swing, but in diode, how steep is this current versus both bias voltage is represented by ideality factor. So if the ideality factor is smaller, then what it means is that you can use smaller voltage to induce the same amount of current. But in conventional diode, ideality factor cannot be lower than 1 due to the Boltzmann distribution. So my research goal here is to overcome these both limitations of the conventional transistors and also conventional diode. So let me start with the low voltage transistors. So alternate transistors are required. Among them, tunneling FET is one of the most promising alternate transistors. Tunneling FET has the carrier injection mechanism different from conventional MOSFETs. Conventional MOSFET operates by thermal injection. As you change the gate voltage, this barrier, potential barrier, moves up and down, and thermal carriers over the barrier basically contribute to the current transport. So therefore, the current is proportional to this exponential EV over minus EV over KT. Therefore, this thermal current, for this thermal current, subthreshold swing is linearly increasing with temperature, and as the subthreshold swing cannot be lowered below 60 millivolts per decade. In case of tunneling FET, the tunneling carrier injection mechanism is not a thermal injection, but it's band-to-band tunneling. Therefore, the band-to-band tunneling is basically it's PN junction and reverse bias PN junction. So if this lambda, which is tunneling length, is small enough, and if we have some positive delta phi, which is the energy difference between the conduction band edge and the valence band edge, then current can flow. Electron can basically tunnel through this tunneling barrier. That's band-to-band tunneling. And this band-to-band tunneling is basically has nothing to do with this thermal tail. So basically, it's cold carrier injection. Even at room temperature, it's cold electron tunnel through this tunnel barrier. So it's subthreshold swing and tunneling. This probability has no dependence on temperature, and subthreshold swing also has no dependence on temperature, and it has no limitation at 300 room temperature. So TFET could replace MOSFET and solve power consumption problem by reducing this subthreshold swing below 60 millivolts per decade. However, there are challenges in TFETs to replace MOSFETs. Basically, the subthreshold swing should be less than 60 millivolts per decade over a wide range of current. But in reality, what people have found that it's very difficult to fabricate this kind of tunneling FET having subthreshold swing, small subthreshold swing over a large range of current. It only has 60 millivolts per decade, below 60 millivolts per decade, only in small range of current. And also, the biggest problem of this tunneling FET is that its own current is very low. The own current at the subthreshold swing becomes 60 millivolts per decade. It's called I60. I60 should be comparable to the MOSFET own current at the threshold voltage, which is about 1 to 10 microampere per micrometer. If the own current is small, that means tunneling delay is long. As large, so basically transistor switch on and off very slowly, because you can think about it as a capacitor, charge the transistor on and off. But if the current is low, then charging time increases, right? So how can we overcome this problem? So to increase the I60, because the on current, people found that from the simulation that if you fabricate this tunnel FET body with a heterojunction, not just a single material. For example, here, the blue curve and the red curve, the solid line, dashed line basically dotted line means the single material channel, silicon, and this solid line means it has a heterojunction body, a TFET body. One indium arsenide has small band gap, and another material, silicon, is large band gap. So if you make this heterojunction with the small band gap material and large band gap material, what happens is that this delta lambda here, tunneling length decreases significantly, and also delta phi on the same voltage. Delta phi increases here from this valence band edge to the conduction band edge. Here, this height increases. Delta phi increase and lambda decrease. The tunneling probability increases. That means the on current increases. So, according to the simulation, if you make this heterojunction body with the small band gap material and the large band gap material, large on current can be obtained with the small SS. So according to this theoretical expectation, in 2015, there was a report that the heterojunction TFET was demonstrated with bilayer MOS2 and germanium. Germanium has band gap 0.66 eV, and MOS2 has a band gap 1.6 eV. And in this heterojunction TFET, they obtained demonstrated subthreshold swing below 60 millivolts per decade over 4 decades of current, which is quite wide range of current. However, I60, which is on current at ISS equals 60 millivolts per decade, is 5 orders of magnitude lower than the what is required value, the required value of I60, which is 1 to 10 microampere per micrometer. So that means this transistor operates very slowly. So why this happens? This happens because of the interface problem between the two material consisting of the heterojunction. At the interface, in this device, what happens is the oxide layer basically increases the resistance so that the on current is very, very small. Besides the oxide layer, defects in lattice mismatch is known to cause this interface resistance so that decreases the on current. How can we solve this interface problem? That's our start motivation of our research. So we use the black phosphorus material. The phosphorus has puckered honeycomb structure. Along the armchair direction, it has very small electron hole mass, light carrier mass, so that mobility is very high. One special unique property of this material is that it's with the number of layers, it changes the band gap. Monolayer, it has direct band gap of 2 eV, while bulk, it has 0.3 eV direct band gap. So what we devise is that we can make natural heterojunction by changing the thickness like this, bulk to monolayer. And then what happens is monolayer, it has band gap 2 eV, and bulk has band gap 0.3 eV on the same material without interface, so that it doesn't have any oxide layer or defect or lattice mismatch. It has natural heterojunction, and if we use this heterojunction, then we can make a TFET, heterojunction TFET, without interface problem. So we fabricate the device with this BP having different thickness, and we use this graphite contact on the monolayer BP to avoid Fermi level pinning and so on. Bulk BP had no gate dependence because of the large thickness, around 100 nanometer. If we gate, only the monolayer band shift up and down. So basically, if we apply positive bias, depending on the sign of the bias voltage, the device operates N-type or P-type. This is also novel points of our device, because a single device can operate N and P-type. So for the positive bias voltage, due to the capacitive coupling between the graphite and the monolayer BP, the band in region 3 under graphite, here monolayer BP band shifts downward. And then what happens is we need to apply positive gate voltage to make band-to-band tunneling occur. So it turns on at positive voltage and negative voltage it's off. So it's basically N-type TFET. When we apply negative bias voltage in region 3 up to the graphite, then due to the capacitive coupling, this band shifts upward in region 3. So to make the band-to-band tunneling between the bulk conduction band, bulk BP and the monolayer BP, we need to apply negative gate bias. So on negative voltage is on, positive is off. So now it's P-type TFET. So sign of drain bias determines N-type or P-type operation. So here's the result, characteristic curve. What we have is both P-type and we demonstrated both P-type and N-type with subthreshold swing over 4 decades of current, smaller than even 30 millivolts per decade. This is the record low value of subthreshold swing in TFET in history. And also, more importantly, we found that I60, which is zone current, is very compatible, very close to the MOSFET on current at the threshold voltage, which is about 1 to 10 microampere per micrometer. So order is very similar. This is the first demonstration of the TFET, both N-type and P-type. There were no P-type, previously there was no P-type TFET that shows subthreshold swing below 60 millivolts per decade over 4 decades of current. And also, I60 close to the desired value. So temperature dependence, as you can see, in the band-to-band tunneling region, which is here, this is a P-type TFET, band-to-band tunneling region, the subthreshold swing is temperature independent. So this slope didn't change with temperature. However, in thermal injection region here, as temperature increases, the subthreshold swing increases, linear dependent on temperature. For N-type operation of TFET, also in the band-to-band tunneling region, this slope didn't change with temperature. However, in thermal injection region, as the temperature increases, subthreshold swing linearly depends on temperature. And this device is encapsulated with HBN and very stable over time, and so it has endurance and also hysteresis free. And we use we use the monolayer, the very thin, ultra thin HBN. In the previous result, we used the 2 or 3 layer of HBN. Now we reduce the HBN here between the graphite and the monolayer BP to monolayer HBN. And what happens is the I60 increased more than about 2 orders of magnitude. So in the record high value of I60 was obtained by reducing the HBN thickness. HBN thickness is very important to determine in the device operation. So for monolayer, bilayer, trilayer, the capacitive coupling changes. So what capacitive coupling increases with less reducing the number of layer of HBN. So small thickness of very small thickness ultra thin HBN is required to increase the the own current. What if we don't use the HBN between graphite and the monolayer BP? Then what happens is current just no longer pass through the black phosphorus below below the graphite, because graphite has much higher conductivity. Now all the currents goes from channel just go through the graphite now directly. So in region 3 here, which is the black phosphorus underneath the graphite, now no longer act as channel. So in that case, device act totally differently. We couldn't.
So this is too long, so we're going to cut that and go straight to the summary slide, and then we'll get back on time again.
Microampere per micrometer. We also demonstrated recently the first Dirac-source diode that operates based on cold charge injection from the Dirac-source, and we demonstrate ideality factor for the first time less than 1. Thank you very much for your attention.